Just a quick overview of 2.1. We talked about the defining, well, two properties that make a relation a function. One that you are fully aware of prior to coming into my class, and then second characteristic or property that you might not be aware of. So if you look at number one, this is not a function because you can say that it's not well defined, or give the justification that if you have an input of 1, it produces 2 different outputs. Now, once again, it's not going to be required for you to understand that, you don't have to write not well defined, but more importantly, so to actually justify that. So if I had an input of 1, I see that 0.5 and 2.5 are both its outputs. Therefore, it's not a distinct output with the same input, and so it's not a function. Number 2, this is a function. You can't really see it because I did some highlighting. Okay. But you can, the domain and range is what I was targeting for you to understand, but this is definitely a function. Number 3 is a function. We can kind of see that there's some asymptotes, maybe asymptotic behavior there as x reaches negative infinity, positive infinity, but we can clearly see that that's a function. Number 4 is where an example where maybe something that you are not aware of before coming to my class, that it's not a function because even though you have a set of x's and you have a set of y's, inputs and outputs that are defined, 3 and 4 don't produce any kind of outputs. So well, also 5. 5 is problematic of the input 5 because 5 produces 4, 5, and 7, and 4 and 5 and 7 are not equal. This is not a function. But also, the second reason is that inputs 3 and 4 does not produce a output. And so when you set a domain, or domain is understood to be all real numbers, or it's given like this, saying that 1, 2, 3, and 4, and 5, then 3 and 4 have to map to something or have to create an output. And so that would be the reason why. And you don't have to say that does not act on all elements of the domain, but if you told me that, hey, these are the inputs, but then don't use the inputs, okay, that does not give you a functional relationship. Okay. Yeah, that's math is life, guys. Okay. Like, hey, I promised you one thing, but I didn't follow through. It doesn't produce any outputs. Okay. You need to, somehow see about finding someone else. Okay. So number 5, okay, not well defined, not a function because 1 produces 2 outputs, 0 and 1, not a function. And then number 6 is a function. Okay, and then we moved on to 2.2. I'm going to do a couple problems from here. I can't get to the top portion of my thing because I'm going to try to move my little thing so that, so I can get to the draw function. And remember, the number one thing that you need to remember about finding zeros is that when you're looking for the y-intercept, then you have to set x equal to 0. If you're looking for the x-intercept, then you need to set y equal to 0. Okay, and so let's just do number 1. Okay, so I'm looking for the zeros, and what does zeros mean? It means that y is 0, so 2, negative 2x plus 3 minus 3. Isolate the absolute value sign, so I end up with a 3/2 on the other side. This is not that much space that I gave you to work on, and then we're going to split that to 3/2 equals negative x plus 3, and negative 3/2 equals negative 2x plus 3. And whether you want to change the left side or the right side to negatives, you're going to get the same answers. Okay, and then when I subtract 3, Oh goodness, fractions are your friends. Or I could just multiply the entire thing by 2, couldn't I? Okay, that would make better sense. Okay, 6x by 2. Here we go again. 4x plus 2, 6. So that's negative 3 equals negative 4x. So this implies that x equals 3/4. And then multiply that by 2. So negative 4x plus 6. So that's negative 9 equals negative 4x. And this implies that x equals 9/4. Okay, so those are the two x-intercepts. Now, I do want it in coordinate form. Okay, so you have to write it in coordinate form. That'll be 3/4. It's just not going to work. What happens if I zoom in up? Yes. Okay, so 3. Oh goodness, I have to do the sideways. 3/4, comma 0, and 9/4. I have to do the slants, which I don't like. Okay, and then when I find, let's go ahead and pick a different color. When I find the y-intercept, I have to set x equal to 0. So I get y equals 2. And that entire thing's going to become 0 plus 3 minus 3. So that implies that y is going to be 3 times 2, 6, 3. Okay, and so therefore my y-intercept is going to be 0, 3. Okay. Okay, so fairly easy. Let's go ahead and do number 2. Okay, the x-intercept, set this equal to 0. You get x cubed minus 2x squared minus 3x plus 6. When you see 4 terms, factor by grouping. Here you go, x squared, x minus 2. So take out a 3x, negative 3 minus 2. That is going to produce 0 equals x minus 2. Take that out. You get x squared minus 3. Split that up. X minus 2 equals 0. X squared minus 3 equals 0. So x equals 2. And x equals plus or minus the square root of 3. Okay. So I can list up here. I have a 2, 0, a square root of 3, 0, and a negative square root of 0. Okay, and then to find my y-intercept, I'm going to put in a 0. So I get 0, 0, 0. You get the c term. Okay, everything is going to turn into a 0. So 0, 6. There you go. Okay, number 3 and 4, I just want you to check the key. Well, actually, I'll just do it here, but then you'll see it anyways. So I did number 4. I did number 3, and I got that. But number 4 is interesting because I'm trying to find the 0, and I ended up with that. And then I told myself, hey, look. Okay, look at this function. It's been moved to left 4 as a square root function, so it's been moved left 4. Okay, and up 2. There has not been a reflection over the x-axis. In order for the square root of x plus 4 to produce a negative 4, and then the dilation multiplication is not going to affect this at all. Okay, in order for that to happen, I came to here and I realized that a square root cannot equal a negative 4. So that means that it doesn't have an x-intercept. No, let's go ahead and write it here. No x-intercept. Okay, I mean, I could have followed through and squared both sides, which I was in the process of doing that. And then I found that the reason I put this problem on the study guide is so that you can see that some of these things, you could do it algebraically, but it doesn't have an x-intercept. Because basically this function has just been moved left 4, 1, 2, 3, 4, because it looked like this before. Moved left 4, and then went up 2. So it can't be 0. It can't produce a 0 output because it's been moved 4 up because of this +2 right here. And so it can't produce that 0. So there's no x-intercept in this. To find the y-intercept, you set 0 equals 1/2, and then 0 plus 4, nice little perfect square, and that's 2 comes out, and 2 times 1/2 is 1. 1 plus 2. So you do produce a y-intercept 3, 0. Okay, but there is no x-intercept. I think I'm just going to do a couple of these problems and then you can check the key for this. This is just a refresher. X-intercept for this function, it doesn't look like it's actually going through 1. So I'm just going to assume, and you could just estimate this, and on the test it'll be exactly labeled. Okay, and so I could estimate a 0.9, 0, and you can clearly see that that one goes through. Okay, the x-axis, so 1, 2, 2, 0. And then over here, which you can kind of think, it doesn't really go through. It's kind of on the outside right there. So I'm going to put, and, whoops, and looks like a negative 2.1, 0. That's the best estimate. The y-intercept is going to be right here. That just went away. And so that is going to be a 0, -2. And then the point of inflection. Remember, point of inflection is the point where it doesn't change direction, but it kind of has a little wobble. Okay, and so it's still increasing right there, but that's a point of inflection, and you could kind of see a cubic function if you know your cubic functions. It behaves like a cubic function there. Okay, it doesn't have any extremes because you see the arrows on both sides. It's not going to have any absolute maxes or minimums because it's all real numbers. Okay, so the extremes, you can just have relative max. We could say this point down here, let's put it in a different color. Okay, blue over here. So rel min, we can say it's like negative 1.5, negative 8, and then rel max is going to be a 1.5, 4, around there. Okay, increasing and decreasing intervals. Increasing. So first of all, let's look at from left to right, right? So we know that all of this, let's put it in a different color. Let's put yellow. Okay, it's decreasing all the way down to that rel min. Okay, and so decreasing interval, we put the x values, we can say negative infinity to, we're putting the x value, so relative min, negative 1.5. Okay, and remember that's parentheses. Okay, and then another decreasing is from this rel max all the way to positive infinity, and that's going to be the union of 1.5 to positive infinity. And then increasing, orange, is going to be this entire middle section. So it's going to be from negative 1.5, the relative min, to the relative max. Okay? And there's no constants. Okay, is it continuous or discontinuous? This is continuous. Is it odd, even, or neither? This is neither. Okay, good job. Okay, so I did, I think we'd stop the video at number 5, after number 5, but I did 6, 7, 8. I did these, the properties of functions on these, and a couple of things that I kind of wanted to point out is that if you look at this particular problem right here, first of all, this is not an inflection point. 0, 0 is not an inflection point, because an inflection point usually has a, because we don't know cubic functions, so if you look at number 5 compared to number 6, number 6, it just goes straight through. Number 5 does a wonk wonk. Okay, it looks like two parabolas. One parabola is x squared, and the other parabola is negative x squared. Okay, so that's what an inflection point is. This one just goes straight through, so that's not an inflection point. Second of all, another way to prove that it's an odd function is, remember, an odd function is a reflection over the y-axis and a reflection over the x-axis. So it's going to negate both the x and y. So if I take a point like positive 2, negative 2 right here, if I take a point like positive 2, negative 2 right here, and if I take the negate the positive 2 for the x, that becomes negative 2, and then negate the negative 2 which for the y, which it becomes a positive 2 for the y. There's a point that exists there, so I know that that's an odd function based on that. Okay, let's see. This particular problem, the extreme is a constant. It's a horizontal line, so I would say that there's an absolute minimum at y equals 2. You can't, because it has to be all of these points in here. So at y equals 2, this entire horizontal line where x is restricted from negative 1 to 1, that is where the constant, where the absolute extreme is. So the absolute minimum is. The absolute min would be that constant interval right there. Okay, this is an even function because there was a reflection over the y-axis, and you can clearly take negative 1, comma 2, and just, if it's a reflection over the y, it's going to change the x's. It's going to negate the x, and so you see a positive 1 and 2 here. For this is a reciprocal function, and it has a relative max right here compared to all of the corresponding, the points around it, and then it has a relative min right there at 0, 1. Okay, let's see. So after that, we're going to move to even, odd, and on the test that you have to do this algebraically, which is going to be, and I made another video about it, but I'm going to go over some of these problems. So let's take a look. So I'm going to drop in a negative x plus 1 and a negative x in here. And so that's going to produce an x squared plus 1. And then when it comes out of that absolute value, the negative 1, I can separate out negative 1s. So the negative 1 could come out of the absolute value because that's actually made up of negative 1 times x. And I can take the absolute value of each one, just like that is made up of negative 1 times x. And then I could raise each of these to the second power. Okay, and so it's going to produce that. What you notice is f of negative x equals the original function. So therefore, this is an even function. Okay, if I put in a negative 2 versus a 2, it's going to give me the same output. That's what it's saying. And this is a reflection over the y-axis. Okay, let's just quickly do these. Okay, so f of negative x equals negative x over negative x squared plus 1. So that's a negative x and an x squared plus 1. And another way to write this, I could take out the negative 1 in the numerator, and I could write it in front, just like that. Okay, so what you see is that f of negative x, so that was f of negative x, equals the original function with a negative factored out. Okay, negative, just like that. So therefore, we know this is odd, and there is a rotational symmetry. Rotational is at 180 degrees about the origin. Okay, for this one, okay, f of negative x, let's go ahead and drop in negative x cubed minus 3 negative x over negative x squared plus 4. So that's negative x. That's going to take it to positive x cubed plus 3x over x squared plus 4. And if you take a look, it kind of looks like the original function. I'm comparing the original function with it. But is there a way to maybe make... No, I did something wrong. Oh, no, negative x cubed is going to be, that's going to remain negative because, no. Oh, why did I put a negative 2 here? Okay, just like that. And so what ends up happening is that I can take, let's use a different color. I can take that out right there, and that's made up of negative 1 times x, and I can raise both of these to the cube power, and that gives me negative x cubed. And then I'm going to multiply it by 2. So that's why it gives me a negative 2x cubed. Okay. And then it kind of looks like it, but then what I could do is I can keep that the way it is, but I could factor out a negative 1. It gives me 2x cubed minus 3x over x squared plus 4. And here I could take that out and multiply it by the negative x, 2x cubed minus 3x over x squared plus 4. And what you notice is that it looks exactly like the original function. So therefore, f of negative x equals f of x. So we know that this implies that it is even, and that implies that the graph is is symmetric about the y-axis. Okay. Let me put a little barrier here. Okay. Whoa, look at the next one. Fun times. Okay, so g of negative x equals negative x squared 4 negative x cubed minus x negative x. I don't know how many parentheses there. 12 times negative x. Okay. That's going to turn into a negative x. That's going to be a negative 4x cubed plus 8x. And then that's going to be minus 12x. Now, if you take a look, okay, is there a way for me to possibly, first of all, I could make what's inside the parentheses look like what's inside of that parenthesis. Let me do it in a different color. Not everybody's watching these videos. Okay, that and that. Can I make those two look the same? Yes, I can. I can take out a negative x. Negative 1. Or negative 1, I'm sorry. And so 4x cubed minus 8x. And then I have a minus 12x. And then I can take this out. And it becomes a negative x squared times 4x cubed minus 8x minus 12x. And then, can I, since we have two terms here, this is one term, and this is two terms, couldn't I take a negative out from both of those? Yeah. So I could take a negative 1 out. Okay. And it becomes an x squared times 4x cubed minus 8x, parentheses, close that parentheses, and a plus 12x. Okay. Oh, wait a second. No. I want to do it this way. That's good. There you go. I took it out of the whole thing. Okay. Now, that just is a negative. That's an f with that. And I got that from inputting a negative x. So therefore, this is odd. And it has that rotational symmetry about the origin. There you go. Okay, now another way to do this is I could have actually just changed the color to purple. Okay, I could have simplified this, and that could have been 4x to the 5th minus 8x plus 12x. You could have simplified it like that. So that's g to the x. And what you could have seen is that since these are all odd, and so I'm going to get a 4x to the 5th. If I popped in a negative, if I did g of negative x, okay, plus 8x minus 12x, and then I could have just taken out a negative 1 from the three terms, and I would have gotten 4x to the 5th minus 8x plus 12x. So you would have gotten the same answer. Okay? Good job. Okay, next one. Let's go ahead and drop in a f of negative x. That's just going to be an, yeah. There's just no doubt about it. This one is, yeah. This one's even. Okay. Therefore, since f of x equals f of negative x, we know that this is even. Okay. And it is symmetric about the y-axis. Okay, this one, if I drop in f of negative x, cube root negative 5x, but then I could separate this out and say it's negative 1 times 5x. Negative 1 could come out, and so f of negative x equals negative 1 cube root of 5x. So therefore, f of negative x equals negative f of x. So we know that this is odd. And it has that symmetric about origin, rotational, 180 degrees business going on. Okay, good job. Okay, so the quadratics, well, this is not over radical functions. I took that out because I was going to cover that with inverses. In the previous years, I covered quadratics and radicals together. This is pretty simple, like finding the axis of symmetry and then finding that x value and then substituting it back into the equation of the graph and then finding the y value of the vertex and then seeing the concavity based on the a. And then the domain range, and then just graphing. But what I want to point out to you is, remember when I said that you can take the a value, okay, and you can figure out the a value just based on, or the points. You can go backwards. You can figure out the next points based on that a value. That is when the a value is pretty clear and it's not really just move the thing. Okay, it's not really clouded by the b value that's inside the function. And in standard form, it's not. It's going to be pretty clear. You're going to be able to see it. In the vertex form, not so much. Okay, but in the standard form, you're going to see a distinct a value. So using that a value, I can plot the next point because that a value to the next point from the vertex just tells you to go up 2 and right 1, and I showed that in the pink, up 2 and right 1. And so if you have that point, then you could just reflect it over the axis of symmetry and get the reflection point. Here, -3 is the a value. And once you plot your vertex, you could just go, you can use the c value for any of these because it fits right into the graph, but you can get the next point by going, since the a value is -3, so that's -3 over 1. So that means down 3 and to the right 1. And so down 3, 1, 2, 3, and to the right 1. And that'll give you that next point. Number 3 is pretty straightforward, except just read the expectation, which is to put it in standard form. Once again, you can figure out the a value based on this next point. I know this graph doesn't have the, is not it by ones, but you can figure out that you went down 1 and to the right 1 to get to that 0,3 from the vertex. So I know that my a value is -1. I could do it algebraically using the intercept form, but it also tells you to put it in standard form, so you have to make sure you multiply it out. Number 4 is so much fun for me, maybe not for you. Number 4, I did it 2 different ways. I first put it in standard form. I put it in standard form because I utilized the axis of symmetry formula, and I gave you the a value, but I thought to myself, okay, I have the c value because c is the y-intercept, and then the a value is given. I just need to find the b value, and the b value, you can get it straight from the axis of symmetry formula. And once you kind of move beyond the fact that you're just memorizing these formulas to get to the same patterns over and over again, but thinking outside the box and actually using the formulas to kind of do things that are unusual for you, or maybe, then this is a very good example of that problem. So I used the axis of symmetry, which was a -1, and then I set it equal to the formula -b over 2a. I gave you the a value of 2, and then I just substituted it. I solved for b, and I got 4 as my b value, and I can just simply write it in standard form because I gave you the a, and this is the a, and this is the b, and that's the c value. Okay, or you could have used the slope-intercept, not slope-intercept, but vertex form. And since I know my h value, I need to find hk, okay? And I know my h value is -1 from the axis of symmetry, and I can use that 0, -1 as my x and y. And I already got the a value already, so I just need to substitute it in for x and y in my vertex form to get the k value. Okay, and then transformations is going to be on another video. Okay, good job, guys.